Thank you and Simon for organizing this workshop. And I would like to thank also the Hertie Foundation for their generous support of this important series of schools. Okay, I'm going to talk about models and theories of memory. Theory are somewhat stronger notion. Most of what I'll describe is models, but theories will be some more rigorous bounds or statements which are quite general. And they're general about memory in distributed neuronal circuits. There are many ways to store memory in physical systems, one of them in our iPhone and our computer. One of the unique characteristics of the nervous system, as the best we understand it, is mostly distributed. Information is represented as vectors in network state space. And most of what I'll talk will be have to do with consequences of this paradigm of memory, that you have the same system stores in a distributed fashion multiple items, multiple memories. This is advantage, but this is also sort of limitations. And those both aspects of it will be clear when I go on along the various topics that I'll discuss. Now, it's quite general, neuronal circuits, distributed neuronal circuits. I am not committing myself or the models to a particular area of the brain, hippocampus or cortex, simply because I personally don't know where memory resides or what types of memory resides where in the brain. Some of the distinguished speakers here claim to know. That's fine. There are data, some suggestions, some models about these issues, but I'm agnostic. So it's quite generic. But there is also an issue of memory, what types of memory I'm thinking about. And one of the first questions that was raised here by one of the students during in the first evening is why we call the school memory and not learning. So what is the distinguishing feature of learning and memory? And indeed, quite often we say learning and memory. There is a journal, learning and memory, and so on. But obviously, every learning has a memory aspect to it. Whatever we have acquired through learning, if it's useful, if it works, it means that there are memory that are lasting for the relevant period of time. However, at least from computational perspective, learning typically, or most interesting applications of learning involve more sophisticated forms of learning rules or learning algorithms or synaptic plasticity rules to implement them. And when we say memory specifically, not general learning and memory, excuse me, we have in mind type of fast learning of experiences or other relevant facts that do not involve in synthesizing inputs. So learning is typically when we learn skills or learn new knowledge or we synthesize inputs into concepts, etc. Whereas here, I hate the terminology, but maybe episodic memory is the more the closer analogy or paradigm. So this is why this is specific about memory, and we will see very shortly the consequences of that, of these restrictions on the type of learning rules that are appropriate for memory. So I'll talk about aspects of memory. Multiple memories are stored as fixed length vectors. So I'm already telling you implicit assumptions that whatever will be learned or be encoded and stored and recalled in the models that I'll describe, all of them will be vectors of representing activation of neurons called population vectors in a fixed length format. Each representing a pattern of neural activation. There will be a storage and recall aspect. There will be the encoding or storage where there is some experience that will trigger changes on the synaptic connections, and we'll talk about what are the changes, how they look like. And then later on, there is a recall, retrieval. I will not talk about recognition. I'll mostly talk about a recall, namely retrieval of the entire memory that was encoded, at least as a goal. This will be done by activating the stored activity pattern in the network. And this is being done by a recalling queue. So there is some, at the recalling phase, there is some initial input or bias or an initial state that eventually leads to the activation of the full memorized pattern as activity, as the network activity. There's pattern completion. Obviously, what we want is not to retrieve the input that is already presented to us at the recall phase in completeness, but the idea is that we want to be able to retrieve or recall memory from corrupted or partial cues. So this is called error correction or pattern completion or maybe association. Anyway, so this is kind of the paradigm in a very general sense, and if we have time over dinner or resting on the slopes, then we can discuss, and it's important to discuss each one of those elements of the paradigm. They are not straightforward, and they can be contested, but that's the way we will go about. So let me go on about more details. So there is a network of N neurons. There is a dynamics and architecture. So let's first I'll talk about the dynamics. So each neuron has this is a very simple version of a much more sophisticated model, but I'll talk about the simplest version. So each neuron at any given time t, I is the index of a neuron in the network, has a synaptic field or input hi of t, and it's composed from a possible external cue or sensory inputs or biases or whatever. This is h0, 0 is the external, and then there is a recurrent or feedback from within the network. So there is summation over the activity of all the neurons in the network. This is Sj of t, and the contribution of each one of the presynaptic neurons is scaled by the synaptic weight Wij. So Wij, the synaptic matrix of the strength of the connection between presynaptic neuron J and postsynaptic neuron I. If there are questions, please stop me and I'll explain. Okay, so at any given time, a neuron performs a linear weighted sum of the input of all, in principle, of all the neurons in the network, or all the neurons that it's connected to it, and then performs some nonlinear input-output. So this is a phi, nonlinear function of hi of t compared to a threshold, theta I. I'll take the simplest, and that determines the state of the neuron at the next time. I'll take the simplest, for simplicity here, I'll take the simplest model where phi is simply a binary threshold function. So if at time t, the input, the total synaptic input is less than a threshold, the neuron will be quiet at the next time. If it is above threshold, the neuron will be active. So it's kind of a 0-1 representation of the activity of the neuron. Okay, are there questions until now? Okay, Yadin, it's okay? So far?
As I remember, yes.
So far, okay, good. So now this is a very simple set of update rules, and the secret, of course, is in the connections and also partly in the input from other sources. But we'll focus heavily on the connections. And the connections start, to describe the connection, we have to start with the architecture. So a very popular architecture. Nowadays, it's extremely popular in machine learning, in all big information technology companies are doing millions of dollars on running networks which are multi-layer. They're called deep networks. So there's a layer of input units, there's the multiple series of processing by hidden units, and then finally the output units. Locally, each neuron is just doing this, okay? But Wij has this layered structure. We will talk mostly, we'll discuss some aspect of it later on, but mostly we'll talk about more, more local network architecture, and in the brain it's mostly recurrent network. So basically all neurons are talking to not all other neurons, but without any layered structure. So there is some internal feedback between all parts of the network. Not every neuron is connected to all other neurons, but there is no well-defined flow of information from one part of the network to the other. So in a recurrent network, the input will be basically the current state of the network. So we'll think about the input as clamping the network in some state. That's the simplest model of an input. And the output will be after we unclamp the network and let it run through its dynamics. Eventually the network will reach a state, or we stop the network at a given time, and what's called the final state of the network will represent the output. So the input and the output are coded by the same group of neurons, basically by the same, by all the neurons in the network. The input is the state of the network as at an initial state. The output is the state of the network as the final state. Yes?
So how do you, is a matrix Wij, is it changing over time?
Yeah, so this is, for now, this is for a given Wij. Now, of course, when we talk about learning and memory, sorry, there is, we have to talk about changes, but we'll come to it. But before that, let me again, even if we talk about recurrent networks, in general, given some Wij, the network can do variety of things, can generate oscillations, can generate chaotic dynamics. The state of possible dynamics is the space of possible dynamics is enormous. We will focus mostly on what's called attractor neural networks. This is now, I hope you'll be able to switch very fast from different representations that I use in my slides. And that's kind of common, but if you're not used to it, then you have to be careful. So now I'm representing not the network in the physical space of nodes and connection, but in the state space. So this will be the state space of two neurons. So imagine this is, and again, not binary because it's hard to write, to draw it in a binary. So imagine this is the level of activity of neuron 1 along this axis, and network and level of activity of neuron 2. So the space of the network, the state space of the network is any point in this two-dimensional space. And now attractor neural network and the dynamics will just flow, taking me from one state to another. In an attractor neural network, they don't do arbitrary things. All the flows eventually converge or reach a fixed point, like the stars here, the stable fixed points. And they're called attractors because they attract all the state in their neighborhoods. These are the stable fixed points. And we'll talk about neural networks that only do this. So in other words, if the input is non-dynamics, if the input is dynamics, the network will follow to some extent what the input tell it in terms of time. But if the input is static and you release the network to do whatever the free dynamics of the network, then from wherever you start, except for this isolated unstable fixed point, but almost from any other state, you will just go to the nearby fixed point. It's called attractor neural networks. Okay, so that's.
Are these stars and the lights of those just like hidden layers in?
No. Again, this is not the physical space. This is not a point in the physical space of the network. This is a point in the state space of the network. So a point here is just an instant of activity of neuron 1 and neuron 2. And in the neural network, this will be n-dimensional space, but it's hard for me to give you a slide with n-dimensional state space where n is maybe million or 10,000 and so on. So a point, so this star is just a privileged state of the network. So this point means that if you are here, if you start the network in this state can be neuron 1 is active, neuron 2 is less active, neuron 3 is not active, and so on and so forth. This is each point here represents the state of all the neurons in the network. The star is a privileged state, so that if you start the network in this state, it will just remain in this state, okay? Persistent activity. Moreover, if you start in the neighborhood of this state, after some time, you'll reach this state and you'll stop there, basically. Okay? Yes?
This distance in this scheme represents actual temporal aspects of the network.
Represents?
Actual temporal properties of the network.
Temporal properties?
It takes more time to get from one point to another one.
Yeah, of course. Well, so think about this diagram as slicing the entire state space, the n-dimensional state space, into regions, which are essentially separate by boundaries, okay? They're not overlapping. And each one of these regions is characterized by the fact that all the points within this region will flow into the fixed point inside this region, in the center of this region, so to speak. Okay, or you can think about landscape of mountains and valleys. Now, of course, if you are further away, close to the boundary, then you will, it will take you more time to reach the fixed point, indeed.
Is that true in an integrate and fire system where you have analog neurons?
That's true also for analog neurons, and not all analog neurons and not all binary neurons are attractor networks, and also attractor networks may have more complicated attractors, but this is kind of fixed point attractors, but this is not specific to binary. It's true also for analog networks.
So how long does it take a neuron with integrate and fire properties? So how long does it take?
Oh, integrate? No. So that's something else. That's talking about spiking networks. So a disclaimer, I'm not talking about spiking networks. I'm talking about rate-based networks. So that's why in spiking networks, it's more subtle. There is correspondence of that, but there's nothing like the neuron is just in the state. Only a dead neuron is just doesn't change, right? When a neuron fires, it always changes in time. The action potential is serious. So in that case, we have to think about kind of looking at kind of averaging over some period of time of the rate of the spike time, the spike rates of the neuron, and then a fixed point means that basically all the neurons fire in the same rate. Okay, so there is an analog of that for spiking, like integrate and fire or other models, but that's again, it will take a whole school for that.
What happens in these states with partial information? Are they so attracted equally?
Okay, I'll come to memory and then we'll discuss it. Okay, so what networks are guaranteed to have this structure, that they cannot do cycles and stuff like that. And there is a famous theorem that says if Wij is the same as Wji, if connections between neurons is symmetric, or all connections between neurons are symmetric, and for binary neurons also that there is no self-coupling, this is the important restriction. In that case, if all the external cues are static, are constant in time, then the network is guaranteed the dynamics to go to a fixed point, which I denote by star, which solve these equations, kind of static equations. So that's the important thing, the symmetry of the connection. Now, it doesn't mean that if the connections are not symmetric, it does not do that. It just means that this is a sufficient condition to guarantee that the network will have this attractor structure, that all the states, almost all the states, will go to a fixed point.
Is it no longer guaranteed if Wii is 1?
In analog, okay, there are experts here, and if I address all the questions of the experts, it will be lovely discussion between us, but it will be bad for most of the students. But I'll be patient for now. In an analog network, it doesn't matter. You can have also Wii, whatever you want. Okay. But again, please, I encourage the students to take the leading role of asking questions. Yes?
Is it necessary to have external inputs?
To have what?
External inputs to observe this dynamic?
Yeah, if the external input is constant in time, like here, then this still holds. If the external input is changing in time, you cannot talk about fixed point, because to a large degree or a small degree, the network will have to follow the dynamics of the external input.
No, actually what I'm asking is the intrinsic dynamics of the network.
This is the intrinsic dynamic of the network. This is this equation. This is the intrinsic dynamics of the network. And it can be in the presence of Hi0 constant. It can be when this is 0, it depends on the network. But this is the intrinsic dynamic. This is, amazingly, this simple rule is enough to generate a lot of interesting computations and functions. Yes?
So is the activation function is stepwise?
Again, it's not, this is general, but for the examples that I'll talk later on, I'll talk about binary networks, and Ed and maybe Alessandro will discuss the case of analog functions.
So it is like a step, the level of activity of each node will be 0 or 1, right?
Yes, that's right. Okay.
Do you have any attractor when the level of activity of each node is either 0 or 1?
The neurons, in that case, the neurons will be either quiet or active. That's it. Okay? If they're active, they're just firing in some given rate, which we call 1. If they're not active, it's 0. It's a very simple, and it's not a matter of principle. Just, I don't want to, to spend time on details which are not important for the core of the story. This is the simplest one. You can, in the afternoon, if you're not going to the mountains, you can run a MATLAB thing of this. It's very simple, 0, 1, and see how it works. So this is the simplest model. Okay, let me go to memory. So now we will talk about, for most of the time, we'll talk about models for memory which have these structures and have connections will be symmetric, although it's not very biological, but let's leave it aside. And they converge, all the states converge to here. But now in the computation of memory, those fixed points have a computational meaning, interpretation as the memory state. So when you converge, or when you start, so let me go through it. Encoding means that we have a synaptic changes that guarantee that memories will be stable fixed points, not, that the fixed point will not be whatever they are, they will be where we want them to be, the memory state. And then the recall means that there is some partial cue that put the network in some initial state in the neighborhood of one of the memories, and the recalling process is completing the memory by converging to the fixed point and activating the entire memory state. Now you can have also partial information, and that's kind of more sophisticated way of initializing the network, but that's not important. We can just live now with this simple paradigm where the recalling with a partial information means that we start the network not at the fixed point, but at some point close to the fixed point. And then if the recalling process is successful, the dynamics of the network will take it to the fixed point, to the correct fixed point. And now, one attractive aspect of the attractor model of memory, which is well known as a Hopfield model, is that at the same time long-term memory model and also working memory model, in the sense that once you, in the recalling process, once you converge to the memory, to the fixed point, you will stay there for a while. It will be a fixed point. It will persist. And that can give you for free the notion, the function of working memory, or at least of this type of working memory, where when you memorize, when you recall a memory, not memorize, when you recall a memory, you can store it in the same network as a working memory for the use as we use working memory for, I don't know, recalling something else, or forming associations, or acting on it, and so on and so forth. So this is one of the great attractive features of this model, that you don't have to you don't have to say, well, I first retrieve the memory and then I ship it to someplace else and do working memory in someplace else. The same network will do it for you. Okay? So now let's go back to the encoding. Okay, so how do we guarantee that the fixed point of the network will be indeed the memory patterns that we want them. So that's the question of learning. And that's a very important question. What are synaptic learning rules that will do that? And what's important for us is the biologically plausible synaptic learning rules. And here is what I said before about episodic versus general learning. In episodic memory, or maybe in other instances of memory which is not episodic, but we learn them fast, we talk about learning that basically it's like online, fast, maybe one-shot learning. We experience something or we read something, can be semantic, can be episodic, but that single experience stores information as memories in our brain. So this is a very strong restriction. There is no, in this case, there is no utility for more sophisticated learning algorithms, which typically are slow trial and error processes. We see one example. We suppose we want to extract a rule from some streams of input and maybe rewards that we get. So the typical story of learning will be we see something, stimulus, we act upon it, we get a reward, we make small changes, another action, another reward, another small changes. We accumulate this over a long time, and then eventually we got the rule of the relation between, I don't know, stimulus and reward, or what is the appropriate action, and so on and so forth. It is, in my view, not a good model for in the context of memory. So I will not discuss, I'll mention briefly, but most of my talk will be restricting to this type of learning. And that's important restriction. We will see it in a minute. Okay, so basically the simplest model that captures this notion of basically one-shot experience that embeds a memory trace in the network is what's known as Hebb rule. And again, I won't go into the history of Hebb, and forgive me, Hebb, for not showing you the picture of you that in every talk you see it. Okay, but anyway, for the sake of time, let me just go to the rule. The rule is very simple. No, it's Hebbian rule. And yeah, it's neo-Hebb or something, you know. Yeah. But again, for the sake of time, let me just describe what it is. So imagine we have experiences that we want to store as memory. So this will be one experience, one state of the network, you know, 1, 0, 1, 0, and so on. This is the state that the stimulus forces the network to be in the time of encoding. Then there is another one, another pattern, another one, and so on. Each one of them we call memory pattern, or state of the network to be memorized. And these are now denoted here by S of t, or whatever, t plus 1, for instance, in this case. So let's suppose we have a matrix of connections at the time t, and now a new memory comes at the encoding stage, t plus 1. So then the connection between the neuron I and neuron J at the next time will be the same as the previous time, plus a contribution which is the product of the presynaptic activity and the postsynaptic activity at that state, the memory state at the encoding stage. So this is if the two, and then I subtract the mean, which is f. So f is the important parameter, is the level of sparsity, namely the fraction of neurons that are active in this memory pattern. And I'll assume for simplicity that all memory patterns have the same level of sparsity. If it's 1/2, it means that half the neurons are active, half the neurons are non-active. Here it is basically like 1/3, 0.3, and so on. And we will assume that all the neurons have kind of mean activity f, the same. Okay, so then we will subtract this because we want to look at the variation of the activity relative to the mean. Okay, so this is S minus F. So if S is 1, then it will be 1 minus F. If F is 0, it's a minus F. And you look at the product of the presynaptic times the postsynaptic activity. Okay, it's called covariance rule because of this subtraction, but that's useful. Okay, this version of the rule has been developed and studied by a beautiful paper by Misha Tzodeks and Feigelman, I think 1987. And we will adopt this for now, because we'll talk about sparse networks, so that's good. Okay, so this is just one-shot learning. You just experience this state in kind of, you want to encode it in memory, maybe it's automatic, then you add this term to the synapses, a new experience comes, you add it, and so on and so forth. So after P time state or P episodes of encoding, you just have this, the Wij, that's the sum of these contributions, with some strength lambda, which is the encoding strength, we'll come to it. Okay? So that's the total sum of learning with Hebb rule P memories. Okay, so mu is the index of the memory, memory 1, memory 2, memory 3, and so on. Now, it's important to consider for our later discussion is that at this stage, after we look at the contribution of all the P memories, all of them come with equal strength and they are kind of equally represented in the matrix of connections. So first of all, this is the distributed nature of the learning rule and the representation. So the same matrix of connection, Wij, is encoding the memory traces of multiple memories. Okay, it's not that one memory is here, another memory is there. No, the same matrix of connection stores all these memories. Secondly, is that there is no time. There is no notion of a memory that was first versus a memory that was last, because they come with equal strength and it's additive, so you just have this. Okay? So at this point, we just talk about a network that the matrix of connection stores P pattern, and we don't care whether which pattern came first, because it doesn't matter. The Wij does not encode the temporal aspect of the sequence of encoding experiences. Okay? Questions until now? Yes?
Do you mean that memory is somehow included in the covariance matrix?
No, the matrix is not covariance matrix. The matrix is connections. Wij is not a covariance. It's the covariance between the neurons will be the result of that. Wij is just a connection. It's a physical connection between neuron I and neuron J. The rule is a covariance rule in the sense that the covariance between the neurons in the encoding in the memory states determine W. Okay? But W is not covariance. W is a matrix of connections. Yes?
I speak as a student. So
Yes, okay, good.
First, I assume that you do not assume that physically the storage of information, quote unquote, is in a synapse, which is the synapse is important for that and it executes the connection, but the storage can be in the cell-wide or whatever.
In the what?
Cell-wide or whatever. It doesn't have to be in the synapses.
Functionally it has to be in the synapses, but it's true that it can be, if there is a mechanism that it's stored in the cell, in the cellular, in the nucleus or whatever, as long as this nucleus knows how to activate in due time.
It has to be expressed in the synapses, but the storage can be some. And
Right.
the second one, just a sort of remark, you use episodic again and again and again, but you use a better term yourself. You
I
use
don't know.
one shot. And that explains
That's fine.
a lot.
That's fine. Forgive me. I'll try to avoid it. Experiences and encoding stages, and that's it. On one-shot learning. Question?
Quick question, yeah. Can you infer from this one that the sparser the network, the stronger the weights, or the average weights between neurons? Or is this
No, the overall strength of the connections is not important. It's in lambda, and you can have some global. The overall strength of the connection is not important, and actually, in some sophisticated memory models, there is, in addition to this, there is some homeostatic scaling to make sure that the connections don't. We'll talk a little bit about it later on, but yes.
Do the attractor states change with the external input? Maybe you already answered it. But
That's what?
so maybe you already answered it, but do the attractor states change with the external input? So if it's dynamic? And
You're talking about the learning rule,
actually I was talking about
the dynamics.
yes.
In the simple model of memory recall that I will talk about, and we can discuss other models, the external input during the recall is just a transient. At the recalling stage, you see a phase, it imposes an initial state on the network, the stimulus is gone, this initial state, the forcing of this initial state are removed, and the network now is running its internal dynamics. We can have more sophisticated paradigms, but this is good for now. Yes.
But since the intrinsic state of the network, you can have different states, right?
You can do what?
You can have different intrinsic states in the network when you don't have external. So isn't it true that the
Well, I think you're using states somewhat different from what I'm using. A state, at any moment, the network is in a state. I call it intrinsic or not, I don't know.
So my question is, isn't it true that this intrinsic state, and what I am calling this intrinsic state, isn't it true that this state defines if the external input is going to be...
All the states that I'll talk about during the dynamics are intrinsic. There is no external input. Okay? As I said, in the recalling phase, you just have some transient stimulus, which gives you the cue, it's gone, and from that on, the network is running through its own dynamics. Okay? Okay. So again, this is a very simple. We can discuss more biologically plausible ways where the stimulus work in memory and so on. But I think it's enough for now to have this. Okay. So here the way it goes. So suppose I want to store in the network this state. So this is a state of, I don't know how many, 1, 2, 3, 4, 10 by 5, 10 by, I don't know, whatever, 6. So each one of them is a neuron. So 0 means that these neurons are 0. White means these neurons 0. Black means these neurons are active. So this is, I don't know, the numeral 1. So this is one state that we want to encode, then another state, and so on. And now, after learning with this learning rule, we try to see whether it works. So here it is the recalling phase. So we start with this state, we see this image in the recalling phase, and we try to guess which numeral this is, which memory it is. Is it 1, is it 5, is it whatever? And so we'll see what the network tells us. So this is the initial state during the recall, and then network neurons starts to update themselves, and then ups, and finally got to this. So this is a successful recall of the memory of the pattern 6. So we started from a corrupted version of it, and then the recalling gave us, reached this state, and this is now a fixed point, which is the corresponding to the memory. So this is just an example of how this will work. Yes?
So I would never have guessed 6 from this.
Right.
Does the network always find the state that is closest to whatever it gives you, or could it also
No. This is just for demo. This is just for demo. It's like Rodrigo said, this is my best neuron. Okay, no, we will talk about it.
My question was similar. I wonder how far needs the pattern to be in the
We will talk about it soon, yeah. I mean, this is, even this is a cheat, but I'll talk about it later on. Okay, but here's the question. So the question is, so what can we say about the ability of this network to actually store memories? So that's what's called capacity. So we have a term of load and capacity. Load is the number of memories, this parameter P, how many memories were encoded in the network, relative to n for now, to the number of neurons. So this is what I denote by alpha throughout my talk. And the capacity is simply the maximum load, alpha C. The maximum number of patterns scaled with the number of neurons that can be stored in the sense that the retrieval will be good. Okay, so what does it mean good? So it means that if I go on and doing this holographic imprinting of more and more memory traces in the same matrix, at some point there will be complete interference or partial interference, and the fixed point of the network will not correspond to the memories at all. Okay, so there are several ways of thinking about this limitation. One is that the basins of attraction will be so narrow that I really have to start very close to a memory in order to retrieve it. But in fact, there is even a simpler scenario of failure, and this is that even if I start from a memory, it will not stay there, that the fixed points will not correspond to the memories. And from theoretical perspective is a simpler measure. So I'll denote alpha C simply by the maximal load beyond which the fixed points of the network will not be the memories, or some of them will not be the memories. So even if you show me the face, I will not be able, well, I don't know, I'll be confused with other faces. It may be familiar to me, but not more than that. Okay, so that's the notion, that's the simplest notion of capacity. What is the maximum number of patterns in this scale above which this structure falls apart, that the fixed points do not correspond anymore to the memories, okay? So actually, this is in most papers, even today you see this, but only the experts among us know that in biology, that's actually the scaling is different because networks are not fully connected. So on top of this Hebb rule, we have to realize that some neurons are not basically physically connected. So each neuron is connected on average to only some number of synapses in the network. So if K is the mean number of synapses per neuron, then the relevant scale will not be the number of memories over N, but the number of memories over connections per neuron. And that's important when we try to speculate about load and capacity for real networks in the brain. Okay? But beyond that scale, it's more or less the same alpha C and the same results. The result that I'll talk about is in the language of alpha C, but you have to remember that alpha C is the number of memories per number of synapses per neuron. Okay. Now you will wonder why it's per number of synapses per neuron. I would guess that the relevant scale is per number of synapses in the network, because after all, we are storing information in the matrix of synapses, right? So why we should not scale it by the number of synapses rather than the number of synapses per neuron? I'll come to it in a moment. Okay. So now, how will I measure the retrieval quality? Forget about the normalization, just to make sure that everything is one when the initial state is the memory. Let's suppose the initial state is the memory for the capacity issue. So I start from the memory in the recalling phase. So I start in the initial state with 1, and I let the dynamics run, and then I'm asking whether the overlap, this function m of t, will stay 1 or converge to something else. So this will be a way to measure numerically whether the fixed point is, whether the memories are really fixed point, because I start from the memory. If it's a fixed point, I should stay there. So this is something which I'll use all the time. The overlap between the current state of the network and the memory state that I want to retrieve. Mu is the memory state that I want to retrieve. I assume that it's most of the time that it's time 0. I start with this memory or close to it, and then I'm asking as the recalling time t, eventually whether it will stay 1 or not. Okay, so this is this final overlap. Okay, and this is the numerical experiment. So this is the load alpha, which I mentioned, and these are for 3 different levels of sparsity. So if the network is not sparse, like 50% are active on average in memory states and also in the network dynamics, so the retrieval quality is perfect, almost perfect, until some value which is alpha C, and then it dramatically collapses. If this network is sparser, like 0.1, only 10% of the neurons are active in each memory, then the capacity is larger, and then at some point it collapses and drops dramatically. And again, the sparser it is, the higher the load is, so the higher the capacity is before it collapses. Okay, so yes.
Y-axis is the proportional.
Y-axis is the final overlap averaged over all patterns. So for each pattern, after I learn, I start the network with pattern number 1. I start the network and see if it stays there. And I measure the final value of the overlap, okay? If it is 1, that's good. And I do it for all the pattern, all the memories. I just query the network with all the memories, and that's average of all memories, okay? So if it is not 1, it may mean that some of the memories are yes, some of the memories are not. But the thing is that this is a very dramatic change. So it's not gradual, okay? Either you are below capacity or you're above capacity. If you're above capacity, it's basically, basically you can throw it to the garbage, okay? It still has some familiarity notion, but as a recalling, it's a failure, okay? And that was, by the way, a glorious state in my own career development. Career development is to actually prove that such a threshold exists in networks, and you know, this is the relevant scale, and these are very sharp, and we can compute analytically, you know, where this threshold appears and what is the error below. You know, if you are slightly below capacity, you know, how much error you expect to see in the retrieval and so on and so forth. Okay, but for now, let me just summarize how this network behaves in terms of the capacity as a function of the sparsity, because you saw the sparsity, the sparser the network is, the higher the capacity. So if it's not sparse at all, so this is a function, this is, it is 1 over f log f, or f is the sparsity, and going in this direction, it means sparser. Going in this direction, it's less sparse. So 0.5 is here, 0.1 is here, and 0.01 is here, and the capacity, the sparsity goes in this direction, f is going down here, capacity goes up here. Okay, so the sparser the network is, and the larger the capacity is, and that's a well-known relation between capacity and sparsity, 1 over f log f. And in this particular instance of this model, there is some prefactor slope of 0.14, but anyway. But it's important, this relation, inverse relation between capacity and 1 over and sparsity, independent of the factor, this is a theory. This is a general bound on memory in distributed systems. And you can show that from information theoretic perspective that there is a bound on this upper bound on this prefactor, but all different models, learning models, if they are successful, they will fight about this number over there, but this relation will be there. And capturing the fact that the sparser the network is, the state of the network, not the connection, the sparser the representation is, the higher the capacity. More patterns can be stored in the network. Okay. Yeah.
I think I missed that. The sparsity means that less connections in the network?
No, sparsity here is not about it's not the sparsity of connections. It is the sparsity of the representation, namely, in each memory, how many neurons are activated, how many neurons respond, or the fraction of neurons that respond in each memory state, okay? So 0.5, it is here, means that basically half the neurons are responding and half not, right? Not sparse, right? 0.5 is basically says in each memory state, half of the neurons are active, half not. Then 0.1, or let's say 0.01, means that only 1% of the neurons are active, are responding to a stimulus or to a memorized stimulus, okay? And then different areas in the brain and different types of stimuli will have different levels of sparsity, and also depends on species, okay? So some areas, if you're hippocampus, it's more like 0.01. In cortex, maybe it's 0.1 or 0.2, depend which areas in cortex and so on. So I don't want to probably Ed and maybe also Alessandro will give you examples of concrete systems, but in general, I would say the relevant numbers will be between, let's say, 0.1 and maybe even a fraction of a percentage in human hippocampal areas, okay? Maybe 0.001, okay, or something like that. Okay. Okay, so now, if we are below capacity, okay, then the basin of attraction are also a function of the load. So if you're well below capacity, capacity is 3.5 in this example, if you're well below capacity, so even if you start from a very small number of Qs, so the starting point is 0.2, 1 is perfect, then this is pattern completion. Then as you run the dynamics, will converge to the fixed point, which is the memory itself. This is why it's 1. So this is a successful pattern completion that is done by the intrinsic dynamics of converging to the attractor. On the other hand, if you are near capacity is 3.5 in this example, then you see that it's harder, right? If you start from 0.4, a fraction of correct bits, so to speak, then you are not doing well. If you start from 0.8, you are converging to the attractor. So the load is not only a capacity issue, but also the closer you are to capacity, the harder it is to retrieve the memory from a partial cube. Okay? Yes?
So in this network, each neuron is either active or inactive, yes?
Yeah.
So what exactly is a time step here? So all the neurons can simultaneously flip?
No, okay, so, no, not necessarily. So neurons, it doesn't have to be synchronous. Neurons flip in their own time, but one means a cycle of update of all the neurons in the network. Okay? So if each neuron is sequentially update itself, so one means n microscopic time scales. One is a cycle of updates of the entire neurons. If you have some clockwise network, then it will be just one time step. More biologically relevant is kind of asynchronous updates, so then one basically means n microscopic time steps.
Okay.
So
but basically from time step 1 to time step 2, any given neuron can
has a chance of updating its state.
Yeah, there's no limit to how many updates there are. Okay.
Right. More questions? Yes.
So the more similar the memories are that I encode, the harder it is to differentiate.
Okay, that's a good question. Here the memories, I didn't tell you about the memory themselves. Are they similar or not? I just told you about the sparsity of them. How am I doing with time? What? Okay, they don't know, so that's good. Let's continue until they figure out. So, but before I answer your question, okay, before I answer your question, let me just address this issue. So, I spoke about capacity in terms of the number of memories, but I'm sure most of you now are in the age of information would think about kind of more information content, which is not the same. And for instance, I said that the capacity is number of synapses, the number of memories is scaled by the number of synapses per neuron. Well, that's interesting. So suppose I have a network with 1 million neurons, and each neuron is connected, kind of physically connected to 1,000 of them. So then it will be like 1,000 memories, right? More or less with some factor, prefactor, but this will be the scale. Now suppose I take a network with 100 million neurons. But still, each neuron is connected only to 1,000 of its neighbors. Well, according to the theory that I told you, the number of patterns that can be stored is the same. Because the number of connections per neuron, the connectivity, is the same in the two cases. Just a larger network, but the connectivity is the same. So something must be wrong. And it's kind of counterintuitive. Now, the answer is that nothing is wrong in it, but we have to remember what does it mean to store a memory? One memory is a state, memorized state of the entire network. So you can ask about not only the number of memories, but the richness of information represented in each memory. So the larger the network is, the richer the information is, the more details you have per memory. So the full picture has to be number of memories, which is indeed limited by the number of synapses per neuron, not by the number of neurons. On the other hand, the information in each memory is the number of neurons, because it is the number of neurons participated in its state. Okay, so the total information content is basically the product of those, more or less. Okay, so capacity is limited by this, but the information content is scaled also by the number of neurons. Okay, so now we can, so this is this kind of diagram, number of synapses per neuron in terms of the number of memories, the capacity, but the number of neurons gives you the number of details in memorized events. If you want the number of associations that you can do that represented in each memory, your pattern completion and so on, and the information is therefore the product of those. Which is the total number of synapses, which is not only the connectivity per neuron, but also the number of neurons in the network. So from this, yeah, go ahead. Sure, no. Go ahead.
Between the previous slide, I missed the link between the two things you said, because first, the Hopkins network you described is 0.14, and the capacity is inverse to the sparseness of the network. So then I can imagine the more neurons I have, in principle, the sparser the network can be.
That's
what is? Then I don't understand what is the link with the number of synapses.
No. Okay, so you're right. I assumed fixed sparsity. You're right that there is another. You make the story more complicated by correctly so that the number, the larger the network is, the sparser you can allow the representation be. That's fine. But what I was discussing is, let's say, fixed sparsity f. I don't change the sparsity level, okay? But I do change the number of neurons in the circuit. But the connectivity, so what I'm saying is, so, I don't know, CA3, let's say, has 1 million neurons and, I don't know, 12,000 connections per neuron, okay? Now, suppose I have a brain where I have 10 million neurons in CA3, but the same connectivity. And the same sparsity, okay? Will I store more memories? No. The theory says capacity is P over K. K is the number of connections per neuron. If the connectivity, the degree of connectivity is the same in the small network and the large network, the number of memories is the same. Again, with the same sparsity. You're right. But if the sparsity is the same, okay? However, it's not so bad because the information that are represented by the same number of memories is larger in the larger network. Because the amount of detail that every memory represents depends on the length of those vectors, okay? So the larger the network is, the more details you have in each one of the memories, okay? That's the point, okay? So the theory is, the theory focuses on the salient limitations of the story, which is the capacity, which is the number of memories. But you have to remember the implications has to do also with with the total information, where the number of neurons, irrespective of the connectivity, enters. Basically, the total number of synapses, because each synapse basically stores more or less 1 bit of information. So the total number of synapses gives you the total number of information. Okay? Given a fixed coding state. Now, if you make the network sparser, as you correctly reminded me, then the number of patterns increase, but not the amount of information. Because the sparser the representation is, the less information the memory is representing. And this you can see because of the entropic aspect. If, let's say, one neuron is active in any state, memory state, and the rest are not active. So then you have only n possibilities of storing information. Either this neuron is active or this neuron. That's a very poor information storage machine. If you have 50%, then you have 2 to the n, almost 2 to the n possibilities. So you have much more information in each one of those memories. So again, also in the sparsity game, you have to remember, you increase the number of memories, but actually the information content is not increased. Maybe also decreasing. Yes?
Can I ask you to help us interpret the information measure? So if each neuron encodes, say, 0.1 to 0.3 bits of information, it's roughly what they encode.
1 bit here.
Yeah, well,
yeah.
In a real brain, it's a little
fine. Okay, yeah.
And I have 300,000 CA3 neurons in the rat.
Okay.
The amount of information you can store is going to be something like, I don't know, 100,000 bits or something.
Sure.
100,000 bits is an extraordinary amount of information.
Good.
But
this is why we have CA3.
But just think of how many things you can separate with that.
That what?
How many items, how much information that is.
No, that's not the number of items. That's the amount of information stored in each one of the states. I don't know what happens here.
It's an extraordinary.
Just a moment. Something happened. Okay. I mean, what can I do?
That's right, but I mean, it's just a remarkable...
It's a remarkable thing, but again, you have to... something happened. You have to remember also that there are simplifying assumptions here about independence, right? That each neuron carries basically. So it's related to correlations, which I'll discuss in a moment. But we have many neurons in the brain, and this is actually what I wanted to close is by showing you that we have enough neurons in the brain. No, this was a punchline slide. Coffee break. Okay, good. So after the break, I'll tell you if you have to worry about that, not enough neurons in your brain or something. Okay, good. Yeah.